So today I thought to discuss about the quiz questions that the second quiz that I've taken, and the performance that you have done in this quiz is shown here. So I asked you 8 questions, and out of 8 questions, I see very few students have done a maximum of 7 questions. So you can see clearly a Gaussian curve that is observed in this test, and this is normal, so we call it as a normal Gaussian curve, and this is actually what we see when we take exams or test of a class. So there are few students who perform very well, and there are some students who could not perform well, and then there is a majority of student called as average, which lie somewhere in the middle. So it should be following Gaussian curve. So let's discuss about the questions that we gave in the quiz. So this was the question. The state space representation of a system is, so you were given a mass spring system, and this mass was experiencing a frictional force which had a coefficient of friction given by B. So on application of a force F, you were required to obtain the state space representation. Since this was in fact a question that I discussed in the classroom, and I obtained the state space. Yes, sir. So it was given in the classroom, and you obtained the state space representation. We studied about it. But in this question, if you look into the options, so the answer lies within the option. There was no need to calculate and find the state space representation, because, as I told you, that in mechanical systems you are required to choose two variables as a state variables, one of which is displacement, the other is velocity. So it was clear that x and v are to be the state variables for this system, which means that option 3 and 4 were ruled out. So you were now required to focus on option 1 and 2, because you have the state variables x and v in first and second option. Now if you look carefully into the option 2, so we see that in this particular option, if you see the state change, the matrix given on the leftmost side, so the order of this matrix is V dot and X dot, while the order that we observe and at the state variable side is, instead of taking it as V and X, we are taking this as X and V. So this is an incorrect way of representing state variable representation. So this option is also incorrect. So the option that you're left with should be option 1. So this was the correct answer. Now the second question is, a state space cannot be used to represent, and I told you that there were certain limitations with transfer function which are overcome when you employ state space representation. And if you check the options, you see that the first three options, the MIMO system, time invariant system, CISO system, are they can be represented by the state space form, and thus option D is correct. Which of the following is a unique model of a system? And this is also, I told you that the state variable representation depends upon what variable are you going to choose as a state variable. For example, I told you that in place of capacitor voltage, since you have a linear relation with capacitor voltage of the charge in the capacitor as Q equal to CV. So any variable that has a linear relation, if there exists a linear relation with the state variable, that variable can also be used as a state variable in place of the variable which it has a linear relation with. So instead of writing, or instead of taking voltage across the capacitor VC as a state variable, you can choose charge in the capacitor as a state variable. And that is why state variable representation does not have any unique representation. While in case of block diagram, you saw that block diagram representation have multiple forms. So you can choose different blocks, and you can represent block diagram in different manners. So this also doesn't have a unique representation of a system. And since signal flow graph is something that is related to block diagram, and since block diagram does not have a unique representation, thus SFG also doesn't have any unique model of the system. While I told you that transfer function of any system, with the condition that it should be a linear time invariant system, because transfer function are applied or are applicable to systems which are LTI in nature. And in transfer function, since you have single input and single output only, so you talk about the ratio output by input, which means that the system should be having only one output and one input. And apart from this, you assume that the initial conditions of the system are zero. Then and only then you can find the transfer function of the system. Thus, it means that transfer function depends upon the internal parameters of the system and not upon the input or output or initial condition. And thus, it makes this transfer function model to be unique. In this particular question, it was asked to identify the forward paths, the number of forward paths, and the number of feedback loops. So, if you see this thing, so I guess most of the people, less than 50%, couldn't understand the loop. So most of the people have identified 6 loops here, but the correct answer is 4 forward path and 4 loops. So if you look into this figure, we see if you start from the input node X and you'll have to go to output node Y, and you'll be moving along the branch arrows. So you'll have to remember the rules that are applicable to SFG for identifying paths or for identifying loops, that there should be the direction of movement should be along the direction of branch arrows, and the movement should be such that no node should be traversed more than once. So applying this criteria, moving from X to Y, so if you start from X, move in the direction of branch arrows. So if you move in towards this node, then again in this direction, then F, then G, then to Y. So this qualifies as a forward path. Likewise, if you talk about starting from X through A, then to B, then D, F, G. This again qualifies as forward path. And then you have starting from A through K, then M, then G to Y is a forward path. Likewise, X through A through K, then L, F, G, then to Y. So this is the fourth forward path. So you see that no node is being traversed twice, and we are moving in the direction of branch arrows. So there are in total 4 forward paths, and again there are 4 loops as well. So if you see, the loops are, you have this loop C, then you have a loop D, E, then you have the third loop M into N, then you have the fourth loop L, F, N. So there are in total 4 loops, and I guess most of the people have wrongly identified as 6 loop because they didn't consider the direction of branch arrows, and the correct answer is 4 loops. If you talk about forward paths, which being drawn here again, so you can look at this. So you are moving in the direction of branch arrows such that no node is being traversed twice. So there are in total 4 forward path and 4 loops. So the correct answer for this question was 4, 4. The next question was the transfer function of the system shown with X input and Y output is. So in this type of question, as I told you, that if you feel any problem in solving block diagram using block diagram reduction technique, so you can apply signal flow graph, or you can convert that thing into signal flow graph and apply the Mason's gain formula. So that could make things easier. If you're quite good expert in looking into the block diagrams, if you perceive them very well, that can only be attained if you are quite good at solving block diagram reductions problems. So you can easily perceive, or you can conclude the answer by simply looking into the representation. But nevertheless, if you convert this into the SFG, for example, you have this question. In fact, let me first try to solve this using the block diagram reduction technique. So you can reduce this, the input from X. This can be given to a summation point. Since you see that the input is common to both the summation points, so I can take these two summation point and represent this by a single summation point with input from X. Then you have an output to the block G2 at the bottom side, then you have another output to the block G1, then this goes to the summation point from where the output is taken, like this. Now you see that this Y is nothing but the output. So the only thing that was not shown here was the connection between this point and this point. So they are not different, they are the same variable. So you are going to pick this Y from this side. So you have this Y connected to H. The output of this block H is then fed back to this summation point with a minus sign. So this is how I can reduce the representation, and I have just simplified this representation. Now what I see is that these are two paths in parallel. Since this is a plus sign, this is again a plus sign, so I can write this thing or reduce this in the form, since this is G1 and G2, so this can be written as G1 plus G2, and this is given to the summation point, and then from this summation point you have output as well as, so there is no need to draw the summation point now, because you have taken the paths G1 G2 as parallel, and this summation point will be eliminated because you have summed them. And from this point you have the signal going through H, which is fed back to the summation point with a negative sign, and this is plus. So now what you see is that this is a feedback loop, a closed loop, and thus you can apply the rule elimination of summing point. So this will give you G over 1 plus GH, where G is G1 plus G2 upon 1 plus G1 plus G2 to H. So we are taking this as plus sign because we have a negative here with H. And I told you that you are going to alternate the sign. If you have this as negative, this will be taken as positive. If you have this as positive, this will be taken as negative. So the correct answer for this question was G1 plus G2 upon 1 plus G1 plus G2 into H. So option 2 was correct. Now the next question is the transfer function of the system is given as shown. So in this particular problem, you will surely feel you're going to face problem using block diagram reduction technique, because you will be stuck in this particular point. You cannot move this point on the other side of the summation point here or at this side. So you will get stuck if you're going to apply the block diagram reduction technique. But if I told you that if you're quite expert in solving block diagrams, so you can perceive what type of signal are going to flow, because the signals are same, and using that idea you can easily solve the problem. But I suggest you, to make things easier, you draw the SFG of this diagram. So suppose that you have input y w, and which is common to both the points, the summation point. So I'll be taking this as common, and from this node now I have the output gone through G, and let us make things simpler, and let us, instead of representing this by a common node, we cannot represent them by a common node, because of the reason that you will have to then show these two signals common to the node. So I think it's not correct way of representing them by a common node. Had these 2 points been connected like this, so in that case you could show them by a common node, but not now. So this node goes through the branch G, then again a node, and from these node you see that the signal passes through again H, and they are all plus sign. We don't see any negative sign in the summation block, so we are not going to write minus H. And from this node we have another signal to this node with H, and from this we have the outputs going to node through which the output Y is taken. So this is the required SFG of the given block diagram, and you can apply in order to find the transfer function the Mason's gain formula, which says that transfer function is summation pk delta k by delta. So you'll have to identify the number of forward paths. In this case, there are in total 4 forward paths. So P1 is 1 into 1 into G into 1. So these are all one gain. Gain is 1 here. This is G. This is 1. So P1 comes out to be G. P2 also is G. P3. Now you'll have to identify the third forward path. So moving, you start from the input node and finish at the output node such that no node should be traversed twice. So you start from W, then you move to this node, then you move to this node, and then to this node. Then from this node you go through the branch corresponding to H. So you go through this branch to this node, then again through G to this node, then this node and the output. So in this particular case, starting from here, here, we see that no node has been traversed twice, and hence this qualifies as a forward path, and the gain for this path will be G square. Likewise, you can identify the fourth forward path starting from W, this branch, then through this branch, this, and this. So this is the fourth forward path, and this will be having gain of G square. But notice that if you cannot take starting from this point, you go in this direction, then you say that I am going here at this node, then this branch, then this branch, and from this I go here. So if you try to take this path as this particular motion or this movement as a path, so it doesn't qualify as a path because of the reason that you reach to a node twice. So this node will be traversed twice if you go in this direction, as well as this node will be traversed. So this doesn't qualify as a path. So you have only 4 forward paths in this case, and now you'll have to identify delta. So delta is 1 minus sum of all loop gains. So how many loops are there? So if you look into the figure, you'll see that in SFG, oh sorry, let me draw the SFG again. So we identified path P1 as 1, P2 as, sorry, P1 as G, P2 as G, P3 was G square, and P4 was also G square. So these are the 4 forward paths that we identified. Now we want to find delta. Delta is 1 minus sum of loop gains. So if you look at this SFG, you see that there is only one loop in the SFG. So for example, if you start from this node, you travel along the branch arrow to this node, then back through this branch to this node, then here in this direction, then back from this branch to this node. So this forms one loop. And if you look, you don't find any other loop in this SFG. So there is only a single loop, and that is G into H into G into H. So this makes G square H square. So we got delta is 1 minus G square H square, and since there is no other loop, hence we will not be talking about non-touching loops. Now you'll have to identify delta 1. So delta 1 is what is the value of delta for that SFG which doesn't touches P1. You have identified P1 as, so P1 was in this direction like this. So the part of SFG that doesn't touches P1 is this branch and these two nodes. So these two nodes and the branch G doesn't touches the path P1, but it doesn't have any loop, and thus delta 1 is 1. Likewise, you can see that for P2 you will be having delta 2 as 1, and for P3 you again have delta as 1, and delta 4 is also 1. So you can see it on your own. If you have any confusion, you can ask me later on. Now if you're going to substitute this into Mason's gain formula, so Mason's gain formula say that the transfer function is how much? Is P1 into delta 1. Pardon? Okay, I guess I don't need to tell you further about transfer function. Okay, transfer function is given as, okay, shall I tell you or not? Okay, transfer function is given as P1 delta 1 plus P2 delta 2. I'm sorry, I'm out of space. Up till P4 delta 4. So I'm not going to write P3 delta 3 and so on. Divide by delta. So if you substitute the values, so P1 is G, delta 1 is 1. So you get G. Then P2 delta 2 is G. So G plus G, then you have G square. So did I miss something? P3. No, everything is fine. So P3 is G square. So this makes G plus G plus G square plus G square. I guess I missed something. All right, let's go on, move further. So this is divided by delta, which is 1 minus G square H square. I missed H square here. So P3 is G square H square, and P4 is G square H square. So this is something that I missed here. So this gives us H square G square P3 G square H square P4. Now this seems correct. So if you're going to simplify this, so you get this as 2G, then plus, so this gives you transfer function as 2G plus 2G square H square divided by 1 minus G square H square. If you further simplify this, you take 2G as common, what you're left with is 1 plus G H square. I seem to be committing another mistake. Let me see, I have solved this. The mistake I committed here is not, it should not be H square G square. This is because I have made a very rough figure, so it is very difficult to comprehend this. So you see that the forward part P3 starting from the blue was 1 into 1 into H, sorry, into G. This is G. G, then you have this term as H, this as G, and this as 1. So the thing was G square H, not H square. Likewise, if you see this, this is also going to be G square H, not H square. So things get wrong if you are going to draw rough figures. So this becomes 2G square H. So you're left with 2G into 1 plus GH. And in the denominator, you have 1 minus GH into 1 plus GH. And this cancels out. So what you're left with is the transfer function 2G divided by 1 minus GH. If you look into the options that were available, you have 2G into 1 minus GH. So this was the correct option. Now the transfer function model is not applicable to. And I told you that whenever you talk about transfer function, it means that you're talking about a linear time invariant system which has initial conditions 0, as well as it will be having only one input and one output, because the transfer function is the ratio of output to input. And thus this will be applicable to linear system, fine. Time invariant system, fine. CISO system, single input single output system, fine. BMO system, multi input multi output. So this is the option. So transfer function is not applicable to multi input and multi output systems. The gain of the SFG is shown as, so this can be, we are talking about the transfer function of the system and can be evaluated using the Mason's gain formula. So if you look into this figure, again you see that there are in total 1, 2, 3, 4 loops. So if let's first identify the number of forward paths. So P1 is 1 into 2 into 3 into 4. P2 is 5. And I guess there are no more forward paths. So there are 2 forward paths. And the value of delta 1 and delta 2. So if you see the first forward path starting from T in this direction, so I don't see any part of SFG that doesn't touches the first forward path, and thus delta 1 gets 1 minus 0. If you see P2, so P2 is this path. So let me choose a different color for this. P2 is this path. And the SFG, the part of this SFG that doesn't touches P2 is this loop. So you have these two nodes and the loop that doesn't touches P2. And thus delta 2 for this comes out to be 1 minus 3 into minus 1, which makes it plus 3, and this gets 4. So delta 2 is 4. While if you talk about delta is 1 minus sum of loop gains. So you identified 4 loops, the gain of which are minus 2, minus 3, minus 4, and minus 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 is minus minus 5. So these are the 4 loops having the respective gains. And if you identify the number of non-touching loops, so there are 2 non-touching loops. So this loop is non-touching to this loop, and there is no other pair of loop which is non-touching except these 2. So you have gain of one loop as minus 2. So it's gain product of 2 non-touching loops. So minus 2 multiplied by minus 4. And this gives you 1 plus 2, 3, 5, 9, 5, 13. 13 plus 8. Alright. So this gives us 14 plus 8 is 22. I think I missed something. Okay, let's see. So transfer function comes out to be equal to P1 delta 1 is 236 into 424 into 1 plus P2 delta 2 is 5 into 4, and you have this delta is 22. So you get this as 24 plus 20 is 44 divided by 22. Let's see the options. No, I think I committed a mistake here. So this should be 1 minus sum of loop gains 2, 3, 4, 5. Fine. And oh, sorry. This is not 13. This is 14. So I committed a mistake in taking the sum. So 14 plus 8 plus 1 is 23. So the correct option is 44 by 23. So this was all, and if you still see any, if you feel problem in solving any of the question or in any question unit 3, unit 2, you can post me or you can ask me directly. I guess this makes clear.